Hello everyone, my name is Niko Saputro. I'm from Mechatronic Department, Parahyangan Catholic University. On behalf of my colleagues Muhammad Saki Gandara and Christian Fredina, I will talk about our research with the title Design of an Internet of Things based low-cost EIAQI based indoor air quality monitoring system. Our motivation to do this research is because not many of the existing buildings have their indoor air quality monitoring. Even I don't have it at my home. On the other hand, most people, especially elderly and young children, spend around 90% of their times indoors. And now during the pandemic, I think they have spent 100% of their time indoors. Studies show that indoor air pollution is more dangerous than outdoor pollution. Therefore, we need an indoor air quality monitoring system to avoid any harmful effects. Moreover, the most previous work that has some indoor air quality monitoring usually use a semiconductor metal oxide sensors. This type of sensor cannot provide easy to read information, because it's only provide the percentage of the pollutants and not the actual concentration of the pollutants. The aim of the research is to implement a standard indoor air quality measurement system that provides an easy to understand indoor air quality information using low-cost sensor, and to integrate the system to ThinkSpeak, a cloud-based IoT analytics, to form an IoT-based system. Our methods for designing the proposed system is as follows. First, we determine the pollutant. We chose two pollutants, carbon dioxide and particulate matter. We also measure the temperature for the thermal comfort. Second, we did the research about the sensor that met with the following criteria: availability, price range, and also it must measure the typical indoor pollutants. After we found the sensor that met all of the criteria, then we start to develop the sensor system, and then we do the calibration of the three sensors to make sure that it's working properly. And then we design the experiment. Based on the experiment design, we determine the source of the pollutant from the experiment. And also we design and put a measurement chamber according to the scenario for the experiment. In our approach, we use an enhanced indoor air quality index, or EIAQI, which is a standard indoor air quality measurement system that is built based on US EPA's standard of air quality measurement, air quality index. Therefore, there will be some conversion process from the sensor reading into the index. As you can see in this figure, first we will convert the sensor reading into two sub-indexes. The first index is AQI, or air quality index, and the second index is the thermal comfort index, or TCI. Then after the conversion, each index will be given a weighted value. After we divide the weighted value, the next step is we determine the smallest weighted value between the two pollutants, whether it is CO2 or PM, or particulate matter. The next step is there will be a conversion of the two weighted values, AIQI and TCI, into one EIAQI index value. Converting the three sensor reading into sub-indexes, we use the following conversion equation. You can see in here all of the definition of the parameters. The result is we can see as an example, you can see it in here. So there will be a sensor reading for carbon dioxide and also for the particulate matters and the temperature. And this is the equivalent index created from this conversion equation. And then we can give a label for each range of index. For example, you can see it here if the index value is between 75 to 100, it is in the status is good. While when the index is from 0 to 25, it is hazardous. Then after we got the index value for EIAQI and also TCI, for each index we give a weighted value. For instance, you can see in here for the EIAQI, the weighted is from 3 to 1 and -3 if the range of EIAQI is from 0 to 25. And on the right side, you can see in here the weighted value is from 3 to 1 and 0. Then to get the EIAQI in here, we do the summation, we add the EIAQI weighted value with the TCI weighted value. So if the total weight is 7, it is excellent. Between 4 to 6, it is good. Between 2 to 3 is bad, and less than 1 is worse status. As you can see in here, this is the prototype of our device. It has a 3 sensor in here to capture the environment information, the pollutants, and also the temperature. And then this is the schematic diagram of the proposed system. And here's the measurement chambers that we built. Basically, the measurement chamber in its side has a hole that we can open or close it, and we will use it for the experiment purposes. We use the measurement chamber for sensitivity analysis to investigate the device performance on the fluctuation of the pollutants and temperature. We define 4 conditions for the experiment. The first condition is when only one side of the measurement chamber is open. In other words, the hole in the one side of the measurement chamber is open, so there will be some flow of air from the outside of the measurement chamber into the inside of the measurement chamber and vice versa. In condition 2, there will be 2 sides of the measurement chamber are open. In other words, there will be more flow of air from inside to outside and vice versa. Condition 3 is when there is 3 sides are open, and the last one, the condition 4, is when none of the measurement chamber are open. In the experiment, we use a candle and put it inside the measurement chamber to generate carbon dioxide, PM, and temperature. Line P1 indicate when we burn the candle, and line P2 indicate when we turn off the candle. As you can see here, when we burn the candle, the index drop quite fast, and then when after we turn off the candle, it takes some time before the index going up again and going back to the original value. You can see here that we for each condition, for the condition 1, 2, and 3, the index going back again to the initial value, but the condition 4, the index never going back to the initial value. The experiment result also show that as the flow of air from the outside into the inside of the measurement chamber getting bigger, the faster the index value going back again to its initial value. So as you can see here, when the only one side is open, it takes 40 minutes. Two sides is open, it takes 12 minutes, and when three sides is open, it takes 8 minutes from the index going back again to its original value after a significant drop. While in the condition 4, it's never going back again to its original value. As an overall conclusion, the experiment in the measurement chamber showed that the proposed monitoring system works properly and can be used for indoor air quality monitoring. Thank you for your attention. Any question or suggestion are welcome.